So far in Chapter 3, we've been learning about shortcut methods and techniques for finding formulas of derivative functions. Well, we've hit the end of the road as far as that goes. We've now got all of those formulas and we've acquired them. So now we begin the process of solving applied problems using this knowledge. And in particular, we're going to be studying something called related rates in this video. And in this sense, there are many problems where quantities are connected and their rates change. So there are many problems where quantities and rates are connected and in that sense related. In particular, here we are going to be studying time rates of change. Now, as a very simple example of what I'm saying by this, if we've got the area of a circle, the area of a circle is given by pi r squared. And if r is a function of time, so if the radius of the circle is getting larger, that means the area will also have to be a function of time. And so what we'll have is some sort of relationship like this. Now, this tells us how these quantities change or how they're related with respect to each other. But if we are interested in the time rate of change of the area, it's going to then be connected to the time rate of change of the radius. And so we've got the techniques that we need in order to be able to study this kind of thing. So for instance, if we were to take the time derivative of both sides of this equation, we will come up with a separate equation that relates these rates. And that's why this section is entitled Related Rates. Now, this is just an exercise in implicit differentiation. We'll get a prime of t is pi times the derivative of r of t squared. So some stuff squared. And we know from the chain rule that that's going to be 2 times the stuff times the derivative of that stuff. And in this sense, quite literally, we have related these two rates. The rate of change of the area is going to be connected to the rate of change of the radius. And so all of the problems that we are going to encounter in this section follow like this. We are somehow going to do a time rate of change of the problem and connect these two different rates. Now, all of the problems that we are going to see are going to involve translating something from words into math. So there's a procedure that I suggest you follow to try to make life easy. Number one, we should draw a picture. We are going to encounter many things given in a verbal or a written description, and it's going to help us understand things if we can draw a picture. Now, at the same time, we're going to be given many different values. Some of those values will change with respect to time, and some won't. So at this initial stage, we are going to label only values that are constant in time. And that's important. As you'll see later, things will change. The second step is that we should label our variables. We're going to identify the given information and label it in terms of what we're looking for. And then what we're going to want to do is identify what we are looking for. And that's going to be important because we need to know what it is we're trying to do all of this work for. And again, I will go through an example to try to clarify this for you. The next step is kind of the trickiest one. We need to have a relationship between our variables. We need to translate the English into math. And then what we need is an equation for the variables, an equation that relates the variables. Now, this equation could come from a lot of different places. It could come from geometry, it could come from physics, etc., etc., etc. But to try to get the idea and give you simple things to practice, for the most part, this will relate to geometry. So once we've got our equation that relates the variables we want, then we need to differentiate the equation to relate those rates. We are always going to use a time rate of change in these problems for the most part, and we'll need to use implicit differentiation in order to do this. And once we've got those derivatives and a formula or an equation that connects the derivatives, then we plug in values for our variables. Earlier I mentioned, look, some of the numbers that are going to be thrown at you will represent things that don't change in time, and some of the numbers that you're going to get thrown will represent things that do change in time. You should have labeled the constants earlier, and now you're going to label the values of the variable to help come to your conclusion. So once you plug in those numbers, you're going to find the desired rate that you're looking for, and then you conclude. You've been given a paragraph, you should conclude with a sentence. So this is a generic roadmap for you. This is a way for you to be able to tackle any problem in this homework section and do a uniform plan of attack. And that's important. You want to build your confidence with these problems because they're all going to look different. And rather than just have all these disconnected cases floating around, what you want to do is have one plan of attack that will let you tackle any problem. And once you understand that there's a framework there for you, it becomes simpler to approach them and you build your confidence in that way. So on the video link here, I've attached a PDF with the first question that we're going to talk about. So this is the spotlight question. So we've got a spotlight on the ground that shines on a wall 12 meters away. If a man 2 meters tall walks away from the light toward the wall at a given rate, how fast is the length of the shadow on the building decreasing when he's a certain distance from that building? So again, this file is all written on the PDF, but what we want to do is take a problem like this and start attacking it. And the first thing that needs to be done is a picture. And this doesn't have to be a work of art. It just needs to get the idea across. And so we've got a person walking on a wall toward the wall. So there's a spotlight on the ground. So there's the spotlight, and the spotlight is shining some kind of shadow. So the person is walking, and the light beams that come off the light, some of them are going to be blocked by the person, and that's why there's a shadow on the wall. And the one that just grazes the top of his head will form the length of the shadow there. So we are told that this distance here is 12 meters, so the light is not moving with respect to the wall. And we are also told that this person is 2 meters tall. Now, all of the other information represents things that do change in time. These two pieces of information do not change in time. And so at that stage, we need to talk about variables. And in this problem, we are interested in something called h of t, which is going to be the height of our shadow. So the height of our shadow is the variable we're interested in. And in terms of our picture, there's h. We want h prime of t. This is what we are looking for. The other information that we need to include is from the given statement. And this says if a man 2 meters tall walks away from the spotlight at a certain rate. So let's say that x of t is the distance from the light to the man. And it's important that we are clear about which one we want. So we'll say that this is x, the distance from the light to the man. And we are told something about x prime of t. X prime of t in this particular problem is going to be 1.6 meters per second. If we were to have picked the distance from the man to the wall as x, then this x prime would not be a positive number. It would be a negative number. And that negative would represent that the distance between the man and the wall is getting smaller. But we don't have that. We have the distance between the light and the man, and that distance is getting bigger. So it makes sense that the derivative is positive. And so once we've got these variables labeled, we could kind of come up with a much more efficient looking problem. And it's really just a problem with geometry here. We've got a right triangle because we're going to assume that the ground and the wall are at a right angle. And now what we need is a relationship. So we need some sort of relationship between x and h. And the easiest way to do this is through the geometry. We could talk about similar triangles, but I find that students have a really hard time defining what that means. So we could just use the fact that we've got right angles and talk about trig. And there's a way for us to connect the variables we've got here just by talking about some basic trig. So for example, the tangent of alpha in this problem would be opposite over adjacent. And so that would give us a 2 over here and an x. So the tangent in this particular problem is relating those two variables. But at the same time, we could have taken that same angle here, alpha, and talked about h over 12. So in both instances, we would use opposite over adjacent. And this would be our equation that relates x and h. Now, this is the part that is different depending on your problem. Every problem will have a different geometric setting, and so every problem is going to be a little bit different. Okay. I could rewrite this as h of t is 24 over x of t. This tells me how the height and the distance are connected. And it says they have an inverse relationship. So that means when x gets larger, so as x gets bigger, the man moves away from the light, the shadow height will decrease. It will get smaller. And that agrees with your intuition, right? The further away you are from the light, the smaller the shadow will be. But if x of t gets smaller, if the man gets closer to the light, then the shadow will get larger. And that's exactly what this equation is telling us. The 24 is there to try to get the precise details correct for this particular situation. So if we want to relate the rates, which is what the question is asking us for, now what we need to do is take a derivative of both sides. On the left, it'll be straightforward, h prime of t, and that's the thing that we're looking for. But on the right, what we're going to need to do is just use the chain rule. And it's probably most straightforward for us here to write this as x to the power of -1. And in this case, the derivative of something to the -1 is negative something to the -2 times the derivative of the something. So what we've now come up with is the equation for how these rates are related. So we've got h prime of t is -24 x prime of t over x squared. Now, a lot of those details are there, but the important one that we need is the sign, right? So if x prime is positive, if he's moving away from the light, h prime will be negative, which means that the height of the shadow will be decreasing. So again, in terms of common sense here, this formula seems to work. So now we evaluate, we plug in our numbers. So we are told that we are told that he is 4 meters from the building. Now that is not x. So remember, x represents this distance, and if he's at 4, we know that 12 is the distance from the light to the wall, and so that 12 has to be x plus 4, and that means x has to be 8 meters. So it's important that you write down your definition and make sure you stick with it. This is what can make these problems tricky. So we're also told that x prime is 1.6 meters per second. I'm going to write that as a fraction. It's going to be 8 over 5 meters per second. And that reason I'm doing that is just because of the nature of the numbers that we've got in this problem. It's just going to make my life easier when I plug things into this formula. And so now I'm ready. I can figure out h prime of t. It will be negative 24 times 8 over 5 divided by 8 squared. One of these 8s is going to cancel with one of those. I could write 24 is 8 times 3, so one of those 8s is going to cancel with the other one. So what I'm left with is negative 3 over 5 meters per second. So I have now figured out the connection. The height of the shadow decreases at a rate of 3/5 of a meter per second when the man is 4 meters from the wall. It's important not to put a double negative here. So if I say the shadow decreases, then I don't need to put the negative in. If I say the height of the shadow changes at a rate, and then I need to put in the negative. So in this sense, I've given you one example of a related rate problem, but how I approach it is going to be how you should approach all of the problems you work on in this section. It will give you a roadmap and give you a strategy for dealing with this.